Hello, everyone. Welcome to our second keynote at the Haskell Symposium. It's my great honor to introduce Richard Eisenberg. Richard is currently a language designer and software engineer at GenStreet, working on the OCaml language and its implementation. Prior to joining GenStreet in 2022, Richard was a core contributor to GHC and Haskell ecosystem. I worked with Richard in 2019, and we had a paper together, which is still, I think, one of my most beautiful papers. Richard earned his PhD from the University of Pennsylvania in 2016, working with Professor Stephanie Warwick. Before getting his PhD, he was a full-time secondary school teacher since he has taught at the Bryn Mawr College and worked as a researcher for Twig. And Richard was a founding director and initial chair of the Haskell Foundation, a nonprofit formed to support the language and its ecosystem. Being a person who worked both on Haskell and OCaml, I'm very excited to hear what Richard is going to tell us. Please take it away.
Thanks for coming, everybody. I was hoping to say that there are seats down in front, but there's maybe one or two, not too many. I don't know. So thanks for joining us this afternoon. Ning Ning actually summarized a lot of the things that I'm gonna start with, but we'll get there in just a moment. So my goal, the big goal of this keynote is to spark conversation, right? So this is about Haskell, this is about OCaml, but mostly what I want to get out of this is more ways that these two communities can talk to each other. This has been something I've been interested in for years before joining GenStreet also, and to foster that communication. So that's really what this is about. But I need your help to do this. So that means that not only is it going to be conversations that happen after this, but conversations that happen during this keynote. So please raise your hand. I'm going to be having opinions in here. Maybe you disagree with those opinions. Maybe you'd like another spin on things. That's great. We can all sort of start this conversation together. I would much rather lose a few slides from my talk and have better conversation than to be able to get through every single small point that I had sort of lined up in here. So please do participate. Okay, I'd like to set a little bit of context here. Again, Ning Ning sort of said much of this. So the context here is that I started to think about Haskell and to get involved with Haskell when I started my PhD. I enrolled in advanced functional programming at Penn under Stephanie Warwick, and right away was just amazed by this language. So I had been programming, I'm not going to do the math, for a while at that point. But what I realized when I learned Haskell is that actually my entire life I've just been programming in Haskell, but in translation. So I spent a while doing a fair amount of Java programming, but actually without realizing what I was doing, I was always trying to do sort of pure functional programming in Java, which is kind of a strange thing to do, but that's just like, of course that's the right way to do it. So when I finally got to Haskell, I was like, this is really what I've been looking for the entire time. And so that was great. So I started a research program with Stephanie, and then pretty soon Stephanie introduced me to Simon, which was great because the research program that I was doing, I wanted to add more support for dependent types in Haskell, and then the first step to do that, I was going to make this template Haskell version of dependent types, which became eventually the singletons library. And to do so, I needed more support in GHC than GHC had. So I quickly decided, this just isn't going to work out. But then Stephanie said, why don't you just, contribute to GHC? And I thought, who, me? Am I going to contribute to some compiler? Well, Simon, among the rest of the GHC community, were very welcoming and really helped me to sort of get into that. And then so what is that, 8 months in, something like that, I made my first commit to GHC, which really was adding extra support for kinds in template Haskell. And so then that started a long collaboration. Simon and I continue to collaborate. We have weekly calls discussing GHC a lot. We've had quite a bit of fun together. From there, I then, a couple of years later, was able to get type and type merged into GHC. So this is really sort of deep in. Those of you who are learning Haskell now may not know of type and type because it's since been deprecated because the features have sort of migrated elsewhere in the extension ecosystem. Then there was this other stretch of time, this is sort of in the middle here, more Haskell contributions, more fun things. I eventually became the initial chair of the Haskell Foundation, as Ning said a few minutes ago. And then sometime after that, something happened. So I, at the same time, I was thinking, oh, it would be nice to sort of experience something a little bit different. And then right around then, something's supposed to happen here. There we go. Right around there, then these three men came and kidnapped me. So this is Ron and Leo and Stephen, who are, I don't know if they're in the room, but they're definitely all at ICFP this week. We started to talk a little bit about Jane Street. That sounded like an interesting idea and a fun new opportunity. So indeed, I taught myself OCaml in 2022 and then joined Jane Street right after that. And then now we are in the process of rolling out OCaml, which is sort of a version of OCaml with a bunch of extensions. So I'm sort of playing the same game over again, right? Take some language, go in, make some changes to it, having a lot of fun doing that. And so with this context, the reason I'm saying all of this, this is how I feel like I do have something that I might be able to say about both Haskell and OCaml. So maybe sort of 10 years in there of pretty intensive Haskell work, and now 3 years of pretty intensive OCaml work. Okay, so with all of this, I have some opinions. Now, here we are. Everyone has traveled here to Singapore, and we do that because we love these languages, and we love functional programming. And so that makes us all a large circle of friends. So I'm going to share some opinions among friends. And so that means that maybe you disagree with me, and that's great, and let's have a conversation about that. So, of course, you will have your own opinions, and that's the beauty of these conversations, is that we can exchange these ideas, see where maybe these languages should evolve to. Okay, so again, the big insight is that these languages have a lot to learn from each other. But that's overbroad. We can't really action that very well. So let's go to a minor, probably wrong insight. So here I have this graph of whether a language is sort of more implicit or explicit at runtime, more implicit or explicit at compile time. And it turns out that the two languages are quite different when plotted here. So this is all sort of a rough estimate, but this is about how I would position the languages. So Haskell is down at the bottom. It's implicit at runtime. What I mean by that is that when you look at a Haskell program, it can be a little bit hard to tell actually what it's doing and when it's doing it. On the other hand, it's quite explicit at compile time. We know what side effects are going to happen. We know often what the types are. People write type signatures in Haskell programs, even though they can be inferred, but people tend to write them anyway. In OCaml, on the other hand, OCaml is pretty explicit at runtime. We often know exactly how an OCaml program is going to evaluate. There is an optimizer in OCaml, so that muddies the waters a little bit, but the optimizer in OCaml does quite a bit less than the optimizer in GHC. Oh, I should also say, I'm going to talk about Haskell. For the most part, I'm really just referring to GHC. Sorry, Leonard. But that's sort of the implementation of Haskell that I'm thinking about. So here in OCaml, I say OCaml is more explicit at runtime. Again, we have a better idea of how an OCaml program is going to run, and yet it's somewhat more implicit at compile time. As we'll see, there's a sort of more type inference going on in OCaml than Haskell has, and as a matter of course, OCaml programmers tend not to write type signatures as they're writing functions. OCaml programmers do write interface files. That's sort of off somewhere else. But when you're actually writing the implementations of your functions, there's usually no types around, which for me, coming from Haskell, was really quite a surprise and disorienting, that I'd be looking at functions and like, what are the types of these things? I don't want to have to do type inference. That is more of a cultural thing. You can write type signatures on OCaml functions, but no one ever does. Okay, Andre does. You can do very close. It's embedded. You say let f colon type equals. I so I can't hear you, unfortunately. So just for the purposes of sort of the recording, I'll try to summarize what Ron said, which is that because the type system in OCaml is simpler than it is in Haskell, we can sort of get away with doing more inference and writing fewer types. There is truth in that. I don't totally disagree. I will say, as a reader of OCaml programs, it would be nice to have more types. But the flip side of that is that we can have, if we have good tooling support, maybe that sort of closes the gap a little bit. I see a hand up toward the back.
So, so I'm just trying to establish the parameters of what you're talking about. When you say that OCaml programmers tend to not write types, is that OCaml programmers at Jane Street tend to not write types, or is it OCaml programmers in general, just like Haskell programmers in general tend to write types?
The two are close to me to say.
So I think the latest count that I saw is that Jane Street has 80 million lines of OCaml code. I don't know how many million lines there are in total of OCaml code, so you can you can guess what the percentage is there. But Code I have seen both within and outside of Jane Street has not had the type annotations, but I admittedly have less experience with the OCaml open source world, and so maybe I have blind spots there. That's a good point. Yes?
When you were talking about explicit versus implicit, you referred to laziness in Haskell and strictness in OCaml. Did you have anything else in mind, or just that?
The other thing that I have in mind is the way that type classes operate in Haskell, in that you can have a function that is parameterized by a type class, and actually what it does at runtime might depend on what type class, what type is inferred for that function. And so this means that sometimes it's hard to tell what a function is doing, unless you've done type inference already. So it's not just laziness.
Ooh. Okay.
Okay, so just, so that there's more reasons to throw tomatoes at me, I've put a couple of other languages up here. I'm not really going to talk about that at all. Okay, so let's talk about runtime. So that's a good segue from Phil. So here we have some differences between the two languages, right? Haskell is lazy, OCaml is strict. Then this middle one, in some sense, these features are quite different, type classes and modules, but they both serve the same role in the overall language design, in that they allow us to sort of do abstractions over types with complex interfaces. So we'll talk a little bit about that. And then Haskell has a very, very powerful optimizer, and this is needed in the Haskell world because of the way that it interacts with type classes and with monads. We really do have a strong need for a big optimizer. OCaml has less of a need for this, and so the optimizer is considerably less powerful. But again, that means that we have more predictable performance. Again, there is an optimizer in OCaml. It's just not quite as far-reaching as GHC's.
It could mean that there's a lot of performance on the table.
Yes.
Waiting for somebody to do that.
Yeah. Yeah, that is true. It is what we're saying. I meant to make this point earlier on about sort of my little timeline thing. So even with my 3 years of experience at Jane Street, sort of when I think about, if I close my eyes and had to choose, what language am I going to write my next project in, it would still be Haskell. My heart is still there. That said, I think because of the predictability of performance of OCaml programs, OCaml is unquestionably the right choice between these two languages, and probably among all other languages too, for Jane Street. So I'm a huge supporter of that choice at Jane Street. Although there is something aesthetically sort of more pleasing about Haskell. I haven't been able to escape that. Okay, so let's look at. So we'll explore a bunch of examples through this talk of code. So here, I conveniently. Oh, and the other thing I should say, there's going to be a convention through this talk. Haskell is on that side. OCaml is going to be on this side. Yeah, I should have placed you and Ron in the right corners. So here, luckily, I could just put this at the top because this works in both languages. But the question is, so I have a bunch of polygons. I want to figure out in these polygons where the triangles are so that I can render them, right? So we're in some kind of 3D rendering engine. Well, in Haskell, I haven't even said what the types are here, but it's a little bit hard to tell exactly what's going on. When will each polygon get triangulated, right? So I have a bunch of polygons. Is it going to be sort of one at a time? Is it going to be all up front? What's my sort of performance characteristics of this? Do I start rendering before finishing the triangulation? That's really going to depend a lot on laziness, right? If I have a lazy structure and if I have a good consumer in render, then we're going to interleave, at runtime, we're going to interleave the rendering and the triangulation. Maybe that's good, maybe that's bad. And does the result depend on type inference? That I haven't written out types for these functions, but if I just look at this little piece of code, maybe render is an overloaded function. Maybe triangulate is an overloaded function, and the way that these operate is going to depend on type inference in some way that's hard to discern from the code. I don't have these problems in OCaml. In OCaml, I'm going to triangulate those polygons and then render the result, right? And furthermore, unless I'm in some slightly less common, higher order setting, I know what render means, and I know what triangulate means. There's not going to be this implicit type class overloading that Haskell has. So it's just a little bit simpler, but maybe slower. Again, unless someone has gone in and performance tuned these functions, but one possibility for slower is maybe my viewport doesn't include some of the polygons. And so if I'm lazy, we would figure out that I never need those polygons triangulated, that we don't have to do some work. Whereas we're going to do all of that triangulation in OCaml. Again, there are ways in OCaml to make this fast again, but it takes a little bit more care from the programmer. Yes, Ron?
Instinct about graphics programming is that the version of viewport limitation that you get in Haskell will be bad. Like that the implicit thing laziness will not do what you want. And if you actually want something performance, you need really direct control and explicit understanding of how you decide what to compute and what not to compute. So the maybe sorry, I feel like if we're talking about writing a graphics engine, I feel like the rely on implicit laziness in the language is maybe not going to work.
I agree with that. This was a 3-word example. I mean, I wanted to get. I'm not saying it scales to reality, but I think it does serve to sort of show that sometimes strictness can be bad, because it does mean that sometimes you compute results that you don't necessarily need. Okay, so having lived in these two worlds, this lazy and this strict world, what do I think of it? I think laziness is a little confusing. I don't think that I'm the first person to say that. There's a talk somewhere out there about a hair shirt on this point. But laziness is kind of good, and especially when it is explicit. So if I am opting into laziness and I know what I'm thinking about when I make something lazy, I think that's quite powerful. And so I would like it to be explicit, except the forcing bit. It's really nice in Haskell if I have a lazy value and I just try to case match on it, that I don't have to explicitly force it. So where should we go with this? I think it would be great in Haskell. I've wanted this for quite some time. So in Haskell, we can label fields of data types as strict, but we don't have a label to make them lazy unless you turn on strict data, and then you can label them lazy. But I just want a mode where I have to label every field of every data type. And I shouldn't have to impose this on everyone, right? This is just sort of a warning maybe that I turn on in GHC. But it would be really nice to force me as a programmer to think carefully, do I want this to be lazy or do I want this to be strict? Because it's just too easy to rely on the default. In OCaml, it would be great to have more laziness, because sometimes that's a really nice feature. And so right now in OCaml, I find it a little syntactically heavy. You have to label it lazy when you're building the thing, and then it creates its own type, and then you have to force it explicitly. Maybe there's a better way there. It's not entirely clear that that works out, because it's, one minus to having pervasive laziness is it also means pervasive checking to see if a thing is a thunk. And so there's some careful design work that would have to be done in order to make laziness a little bit more ergonomic in OCaml. Okay, let's get on to another example. So here I have some input. Again, I'm not really saying what the type is. I'm going to filter some predicate P over it and then map some F. And the question I have is, there's an intermediate structure here. Does that get built? Well, in Haskell, probably not, but it's a little bit hard to know, right? I'd need to know what the types are involved. Do we have rewrite rules? That's the citation that's up there, very small. Do we have rewrite rules in effect? And actually in Haskell's, in GHC's standard library, there's this very carefully constructed, good producers and good consumers, and we have to make sure that all of these things chain together well, and it takes quite a bit of work to maintain. But it does mean that we get deforestation a lot of the time. That's what it's called when you don't get the intermediate structure. It's called deforestation. And it is quite powerful, but we have to just make sure that we've done the right map and the right filter, and if you implement your own from scratch, then it probably doesn't participate, so it's a little bit fiddly. And in OCaml, yes, you get an intermediate structure. Again, predictable performance on the right, but maybe not quite what you want. Okay, so what do I think here? This one's really hard. I personally can't seem to come up with a strong opinion on what's better. Do I want a powerful optimizer that means I don't really have to think about performance most of the time and I just get decent performance out of the box? Or would I rather have something where I can really understand the performance and predict it in advance? And these things sort of play against each other. Again, my sort of the stance I said earlier still holds. For Jane Street, I think the answer here is pretty clear. But in general, it's a little bit hard to know what I think here.
Yeah, but a Haskell story is pretty good here because you can have inspection testing. So you can add to your test suite that this exactly deforests and fuses.
Yes, absolutely. And then there was another point over here.
So in both Haskell and OCaml, the solution to this, in my mind, is simply don't use list, use sequence, or they both sort of boil down to you're probably using the wrong type if you care about materializing intermediate structures or not.
Sure. What if you have arrays? I mean, this sort of the same challenges apply. I saw there was a point in the back, Matthew.
So what if the types told you exactly where there will be an intermediate structure and where there won't? Would you be happy with that?
I'm not sure what you mean by the types telling you.
Well, so there is work where it's a variation on stream on all the stream fusion work that you didn't mention, but which is alternative to the reference that you gave. Where it's the fusion will happen so long as you inline everything, but there's a specific type that will show you. It will be a type of buffer, and there you know that there will be copying going on, but otherwise no copying so long as the inlining happens. So you can then ask the compiler you could basically maybe force the compiler to inline, and then you have a guarantee that things are going to be copied, but only where you think they are, because the types are telling you that.
That sounds pretty good to me. Again, to me, I think the key thing is predictability. And so if you're operating in a type where you know that there's never going to be intermediate structures sort of no matter what you do, because you'll get an error if you chain together the wrong functions that would produce an intermediate type, that sounds pretty good. Okay, let's carry on here. And this connects back to Jeff's point, is that you need to check your work. So I think that this site is lovely. I have nothing to do with it, but there's this website godbolt.org, and it allows you to type in some code, and then you can see the assembly code that's generated by your Haskell or OCaml code. It supports many other languages also, and so it's a great way of just telling what's actually happening under the hood. Okay, let's move on to, that was some runtime stuff. Let's move on to some compile time stuff. So I kept trying to come up with a way of saying like my initial stance here without it being opinionated, but I failed. And that is that OCaml type inference tries harder. So we just get more inference in OCaml, but GHC is more predictable. So like this is sort of the opposite problem that we have in the runtime stuff, is that I find even after a bunch of programming in OCaml, I just find what it accepts and what it doesn't accept to just be harder to anticipate from first principles. Not that there aren't rules. There are rules. It does have principal type inference. We can figure it out in the end. Just like in Haskell, eventually you can figure out exactly where things get forced, even in sort of nested lazy structures. It's just harder. So let's look at a couple of examples here. So this first one is actually, everything is already up on the slide, in that this has a type signature, right? Haskellers will write a type signature on that function, even though it's a pretty simple function and its type can be inferred pretty well. Oh, by the way, I've turned off numeric overloading for this talk. There's no overloaded numbers in Haskell.
But that is cultural, right? You could delete the first line.
Yes, it is cultural. But the languages are as they are deployed in the world, which includes their culture. Yes?
This to me seems like a quite deep cultural difference, because my immediate thought is, how did you write this function if you didn't even know what type you set out to implement?
Well, you did. You just didn't write it down. Yes. So when I started doing OCaml, that's exactly how I felt. I've become more used to it over time, but I still, the good news is that especially nowadays there are powerful language servers in both languages that allow me, when I look at a function, I'm like, what is this? And I'll just quickly query its type, and then that's just as good as having it in the source code for the most part. Having it in the source code also means that you have it available in review contexts and when it's up on GitHub and sort of in other places. So I still think that having the type written out is a little bit better.
So there clearly is this cultural difference, but I wonder how much of that is just a purely ergonomic thing. In terms of OCaml, you can, in theory, write the type signature there, but it's kind of ugly because it's sort of stuck in the middle. It's really convenient to be able to stick that signature beforehand. Do you think that's the...
Maybe. It could just be an ergonomics thing. So those of you who don't know OCaml will see an example on, here we go. And so we'll see sort of a slightly better example in like 30 seconds. So here, if I write that code in Haskell, well, we say that this should work for any A, and it's not going to work for any A because not every A supports plus, so that doesn't compile. Over in OCaml, on the other hand, so this demonstrates Sam's point, I think, in that here I have this type signature, alpha to alpha, that's how that's pronounced in the OCaml world, and then I have to have this sort of fun. I can't, it's just not quite as smooth looking. But this is perfectly fine in OCaml. And that's because a type variable in OCaml means I just didn't bother to write down this type, but you figure it out for me, compiler. And so add1 will get accepted with this definition. It'll be given the type int arrow int. It's not given the type alpha arrow alpha. That would be bad. But again, this is quite different from the philosophy that exists in Haskell. So in OCaml, we can do better. And if I write for all alpha, OCaml just omits the word for all, but it still has this syntax. Then indeed this will get rejected. Right, and so this extra for all alpha is closer to the Haskell type signature, but this is very rare, at least in my experience in OCaml code. Ron.
So one, I think, important cultural and technical difference that I think is very important when you think about how types show up in the language is signatures, right? Like I think maybe like the single sneakiest best feature of OCaml is that, which some people who are not OCaml programmers think is a bad thing, but I think it turns out to be a great thing, is separate interface files. And people carefully and lovingly create interface files that say at the level of a whole module, like what are the types here and what are the signatures of all the things, and that's like a very good and very ergonomic part of the system. And I think part of the reason why people are not writing the type annotations inside the implementations is there's another place where they are writing them.
Yes, that's a really good point. So in this talk, I'm focusing on sort of the ML files and not the MLI files. But I completely agree with what Ron said, which is that when you have, because in OCaml, you have these separate files that describe the interfaces to your modules. That's the place where the type signatures go. And at first, when I started to do OCaml, I was like, I have to repeat everything, and this is kind of annoying. No, actually, it's great. Because it means that I have one place I can look at to understand what is the interface to this thing. Haskell has this somewhat. So unfortunately, I don't have a slide on this, so I'll just sort of do it live a little bit. But Haskell, you can write at the top of a Haskell module. You write down all of the things that you export from that module, and that has some of this flavor. But it doesn't. You don't have the types there, so the types now are sort of distributed throughout the module. It becomes sort of harder to navigate. Whereas in OCaml, you do just have this separate file, and everything is right there. And there is repetition, and that does take real programmer time as you're working on it. But in the end, I think the ability to read the code is worth that time spent in producing the repetitive code.
I just wanted to point out that the original design of Haskell had the ability to have handwritten interface files. The .hi files could be written by hand.
Ah, that is news to me. I did not know that. Thank you.
I think one of the reasons that we also don't write types at the structure level is that in writing type variables, there's actually 3 different syntaxes we can use. And there's not actually one most general syntax that we can use. And there's like subtle cases where they do work and they don't work. And it's not clear to users why.
Yes, that's true. So instead of saying tick a dot here, I could have said type a dot, and that means something subtly different. And that's not something I'm going to really explore in this talk, but that is true that there's a bunch of different ways of doing this, and they're all just slightly different from each other and a little confusing. Okay, let's move on. So let's look at some GADT inference. So over here on both sides, I declare type T and a constructor that constrains the argument type of T. So over in Haskell, that's going to be rejected. We don't know what type to give to F. We can't tell, should it go from TA to int, or should it go from tbool to int, or something like that. Over in OCaml, sure, we can accept that. Again, this sort of goes back to my type inference just tries a little bit harder. And so here we can infer what type F has and say that it just goes from bool to t. It makes that decision. It does have principal types, and that's it's slightly subtle to. What was that? Well, this particular definition of F doesn't support that because it doesn't have a locally abstract type A. We could talk more about that later. Yeah. This still is this is not my favorite area of OCaml type inference. Okay, so what if we had 2 different constructors? So now it's tbool or tint. Well, still on the Haskell side, we're not going to know how to deal with that. And then now over in the OCaml side, once again, now this has become too complicated for type inference to deal with over in OCaml. So the way to get a GADT pattern match to work on OCaml is to use this extra type construct. But let's first look over at the Haskell side. So on the Haskell side here, now I've given a partial type signature to say that I definitely want this to take a TA. It's not going to be a tbool or a tint, but a TA. But the result, I'm just not going to say what that is. So this is a less used feature in Haskell to be able to just sort of leave out part of a type. It's actually quite a common thing to do in OCaml, to just give part of a type. And you would think, oh, well, this clearly returns an int. But Haskell says no. And that's because maybe it doesn't return an int, maybe it returns some type family that operates on A, and it is true that returning int here would not be principal. But most of the time, we probably just want this to return an int. And so over in OCaml land, it indeed just returns an int. Well, in OCaml it is, because OCaml doesn't have type families. So this goes back to it's a slightly weaker type language, so we can get a little bit more from it. And so in answer to sort of Simon's point earlier, it's like how could we have inferred bool t arrow int on the previous slide? Well, the only way to sort of do proper GADT pattern matching is to have one of these type A declarations to say, here I have the type that's going to be discerned. And if you don't write the type A, then you don't get a proper GADT pattern match, so it was still principal. It's a little different than Haskell. Okay. What was that? That does not need a quote, no. This goes back to Alistair's point of there's multiple different ways of doing things, and they're all slightly different and confusing. Okay, over here in Haskell, we can finally accept this if we label the return type as int, and now we've said enough about this GADT pattern match in order to accept. Okay, so let's talk about type classes a little bit. So here in Haskell, I have a function, and obviously I don't know what action 1 and action 2 do. But what also I find slightly alarming is that I don't even know what the invisible semicolon does. So what no one in the room sees is that there is a semicolon right here between the two lines, and because the do inserts that semicolon for us. But I don't know what monad this is operating in. And so different monads have very different behavior about how they string together one line to the next. And so here I'm going to have to use type inference, and maybe action 1 works over any monad, but action 2 works only over a specific monad, so then I have to look at action 2's type, figure out what monad it works in, and that must be the monad for the whole do. And this causes a challenge for readers of this code. And so that's why I often, when I have multiple monads near each other in Haskell code, and I write do, I'll just have a little comment saying which monad I'm using. And actually, Haskell has recently gotten, or not so recently, but qualified do, which allows you to sort of specify a little bit more directly what monad you're operating in. And so this can be sort of a slightly unpleasant part about type class inference. Let's look at modules for a sec. So here I can have a module that looks like this. And modules are a really powerful mechanism in OCaml because I can take different interfaces and combine them in different ways and then build up large complex interfaces by mixing others together. The minus is that when I actually use this, figuring out what is exported is quite a challenge. And so there's tooling to help with this, but in practice, sometimes you end up jumping from MLI file to MLI file to MLI file, trying to figure out what's going on. And I'm seeing sort of knowledgeable nods from some of my Jane Street colleagues on this point. And so again, with a language server, we can do a lot better, and in fact do that, and so we rely on that. But modules are powerful, but with power comes oof. So let's see. We should get, okay. So what about the comparison between these two? So as I said earlier, that both of these features give us powerful ways of abstracting over types with complex interfaces. And so should we have type classes or should we have modules? Well, I think we should have both. And what's fun is that both language communities also seem to think that we should have both. Way back in 2019, I proposed local modules for Haskell, which admittedly is not modules in the full glory that OCaml has, but rather is more of a sort of a namespace mechanism. But it would really quite allow us to organize Haskell code a lot more than it is now. And then also, a number of colleagues put together a proposal for modular implicits in 2015 as a feature for ad hoc polymorphism in OCaml. So this is not quite type classes, but it gets much of the way there. And so what do I think that we should be doing as communities? Well, in Haskell, it would be really nice to have better namespace control. So that local modules proposal, it sort of ran a little bit of ground on technical issues, and I'll admit I sort of ran out of steam trying to sort of push that one through after sort of the 10th random small technical issue. The broad idea was great, but the last 2% was really a struggle. And so I don't really think that Haskell needs proper modules in the way that OCaml has with sort of a functor discipline. I just don't think it's needed. I think it's a solution to a non-problem that in Haskell. It might be nice, but it would add a lot of complication.
But it's a solution. Why is it a solution to a non-problem? In OCaml, it's a solution to a problem.
So hold that thought. So in OCaml, I think that we should add type classes called modular implicits, but without the global coherence property that Haskell has. That global coherence property in Haskell is very anti-modular. And that would just sort of really go against the grain of OCaml. But the modular implicits proposal sort of happily keeps that property away. So right now, there is active work by Didier Remy and Samuel Vivien on working on modular explicits, which is a precursor to modular implicits. So this is actually happening, and we have the little OCaml logo because we expect this to become part of OCaml at some point. Maybe it'll also become part of OCaml at a similar time frame. I do believe the OCaml community has good support here. And then this is more of a direct answer to Simon's question, which is OCaml does not have support for higher kinded types. And this means that, but sometimes we want to be able to abstract over something with higher kind. So we might want to talk about a collection in general, where we leave the element type of the collection sort of polymorphic, but we want to be able to talk about all different collections that are polymorphic. The only way to do that in OCaml is to use the module mechanism. And so because Haskell has higher kinds, Haskell has much less of a need for modules, for sort of the functor-based module system that OCaml has. It remains to be seen once we have higher kinded types, and once we have modular implicits, then how much do we end up using the module system versus these other features? I think that there's some experimentation to be done and some more understanding to be found there. Let me just say, so this is Kuba Bakursky, who actually implemented higher kind of types as an intern project at Jane Street last year. So that has not yet been merged, but I hope it will be soon.
Perhaps I can just add a comment here. I think the whole higher kind of type thing, it kind of slipped into Haskell fairly early. It was Mark Jones, who was largely in support of then we can have type classes that abstract over monads. I think that was a sort of killer app initially. It seems to be that feature alone has given birth to an enormous amount of creativity in Haskell space. You can't talk about categories and monoids and lenses and bifunctions without high kind of type levels. It's amazing how much you can do when you have that one feature. And it turns out that unlike other type system features like invertibility, it's really easy to do. Except you do have subtyping, which you do.
Well, we do have subtyping, but the problem is more that we have subkinding.
Yeah.
We could talk more about that offline, but
So anyway, this thing is that people often say, what's distinctive about Haskell type classes? For me, high-kinded type, that's a huge deal.
yeah, I agree. And so it's one thing that I'm looking forward to seeing how once we have higher kind of types in OCaml, how does that change our library structure? There's a point over here.
What's the use of adding higher kinded types when you can't talk about their behavior? Like, so your point was, we want to reason about some form of collection that's parameterized, but that's not very useful in itself if you can't talk about but it also has a map function as well. And so really you want both to talk about some form of parameterization of the type and its behavior, which is what you get with higher kind of types and type classes.
Yes, I agree. Okay. Yes. Yes, or modules, which is why right now they're tied into modules.
I guess my question is, we are almost there with modular explicits, so why do we need high
Oh, because we still need to be able to sort of talk about the higher kinded types. I mean, as in, I want to be able to talk about a collection just in sort of in abstract terms, and then that requires some amount of abstraction over higher kinded things. We can maybe talk more later. Okay.
The slide says Haskell, but not proper modules. But I thought we had Backpack, and no one uses it. So we do have proper modules, right?
So maybe I phrased it more sort of provocatively than I needed to. When I say proper modules, I really mean sort of OCaml style functors, which are functions that take in a module and produce another module. So one strange thing is that both Haskellers and OCamlers talk about functors, but they're totally different concepts. That's true. That's true. Interestingly, a project that Jane Street is under at the moment is essentially taking Backpack and porting it over to OCaml. So this is so in OCaml world, this is called parameterized libraries, and it is more ergonomic than some uses of functors. I don't have slides on this, so I don't want to go sort of too deep into that right now. But interestingly, we're taking very similar ideas to Backpack and moving it over into OCaml. Okay. Okay. So this is a particularly sort of favorite subject of mine, to sort of think about purity. Even after 3 years of programming OCaml, I continue to be surprised by mutation. So that said, I want to think a little bit about Haskell and about purity in Haskell. So in the GHC compiler, we have this operation called zonking. How many people here know what zonking is? Okay. Just a handful. I'm surprised to see sort of more of an OCaml person raising your hand about zonking. This is very simplified. Don't try searching GHC's code for this. You will not see it. But in GHC's internal representation for types, we have the possibility that a type is a unification variable, right? I'm in the middle of type inference. I don't know whether something is going to be an int or not, and so maybe eventually I learn that it's an int, and then I can fill in this IOREF. IOREF is how Haskell spells what OCaml just calls ref. And so here it starts out empty, and then might get filled in with something like int. But then the problem is that now to be able to see that a type is really an int under the hood requires that I operate in a monad. Whereas so many of the algorithms that GHC has really don't care about the difference between the type variable alpha and the int stored inside of it. And so it means that GHC has to be quite careful about this operation called zonking. Oh, zonking is when we take the alpha, take the unification variable, and replace it in a structure with int. It's really just applying a substitution. But it's this idea that as we've accumulated the substitution, that instead of being stored in some kind of substitution structure, it's just stored in memory by using these mutable references. But it's the act of essentially applying that substitution. So because we have to be careful about this, there's a lot of time that Simon and I and others have spent trying to figure out exactly when do we zonk, how do we want to zonk, and then we had to come up with the purely well-kinded type invariant and such, because sometimes we're in a pure context and we don't have access to zonking, and it's just all a little bit uncomfortable. And so it's kind of annoying. But not having purity is just worse. I will keep the purity and keep the annoyance, as opposed to over in OCaml, it's really quite hard sometimes. When I go into a new code base and I see some function operating over some large structure, is it mutating that structure? Does it matter whether I apply something before or after that other operation? I really don't know, because I can't tell the difference between side-effecting operations and pure ones. And so this I find is sort of a challenge in OCaml programming. But maybe with some of the ideas that we're coming up with in OCaml, maybe we're going to improve on this. So I gave a couple of sort of mini talks during the week out at the Jane Street booth. sort of showing how new features that we're adding to OCaml control purity and allow us to have this notion of referential transparency. That's really what I'm after, is referential transparency in OCaml. And this is still very early days for this feature. Although the compiler parts have been implemented, there's a lot of library work to do, because now we have to go in and essentially label all the pure functions as being pure. And so we haven't done that yet. So you can't even add two numbers together purely in OCaml yet, even though the compiler sort of understands this idea. But there might be sort of an interesting middle ground here that we can sort of navigate. And I'll be really curious to see in a couple of years, as we continue to develop this feature out, how this weighs against purity as it exists in Haskell. Okay. A few maybe smaller points about scope in the two languages, because this is another area, and this is an area where my own opinion evolved after programming in OCaml for a bit. Okay, so this is actually, this first example did not evolve. So here I have a sort of a terrible way of computing the next. If I have two numbers in the Fibonacci sequence, I want to compute not quite the next two numbers, but sort of the next pair of numbers, sort of move one up. And this computation does it. This is very silly code. But over in OCaml, this just kind of makes sense. I can shadow n2 and I can shadow n1 and everything works. It's fine. If I write this in Haskell, I get a horrible loop. Right? And that's because every Haskell let definition is recursive by default. In OCaml, if I want a recursive function, I have to explicitly say, please make this recursive. And so OCaml, we just get nice shadowing, things are good. I think recursion should be explicit. And this was true. I thought this some time ago. I'm not the only person to think this. So there was a proposal from, when was this? 2021, to add, again, optionally, the ability in Haskell to sort of mark things as needing explicit recursion. And I was a fan of it back then, again, before Jane Street. There's a question in the back.
Oleg Kiselyov has a really fun identity monad trick, because if you use do notation in the identity monad, then you can have non-recursive let bindings.
Yes, that's true. So we can use the identity monad to avoid this problem, because in monadic notation, that is not recursive by default. But that's a bit heavy, I think, to get around to sort of a scoping thing.
But it is, the recursion you showed is explicit because you're shadowing, right? So like you're calling n1 again. You've chosen to shadow a variable that's bound by a let, and so because you've chosen to call that, isn't it going to be explicitly recursive?
In OCaml?
No, in Haskell.
Well, actually, I mean, going back to the, where has it gone? Here it is. I mean, this Haskell code, both the original n1 and n2 never get used. Those are unused variables. See, it is confusing. That's a good point. Yeah. So in OCaml, OCaml supports equi-recursive types, which is a bit strange. Also, that's not something I have a slide on. But yes, that's a good point. No, in Haskell we don't have that. Oh, that's not what you're talking about. You're talking about the fact that in a type declaration in OCaml you get recursion by default. Oh, that one I'm not sure about. Probably better not to have that on by default. But many types are recursive, but it is awkward, especially when every type is just named T. Yes, but yes, that's true. So types. So in OCaml, normal variables are not recursive by default. Types are recursive by default. Modules are not recursive by default. And so there's keywords. There's a rec keyword to make them recursive and a non-rec keyword to countermand the recursion on types. Probably this could be a little cleaner. Okay, where were we? Over here. Okay, so here's another difference between the language, and this is the one that I said sort of evolved as I programmed in OCaml. So here I have a case of a function f that when I initially defined it, I wanted to have some accumulating parameter so that it can be more efficient, say. But then the version of f that I want to expose, we don't want to expose that accumulating parameter. So here, I'm just going to define a new f that calls that first one up there. Of course, that makes no sense at all in Haskell, and that's because Haskell does this sort of global inference to try to figure out what order your definition should be in. In OCaml, on the other hand, this is just fine. Things just work from the top down. And at first, I thought, this is kind of annoying to have to always work in top-down in OCaml. But having seen a number of different ways that this has played out, I think OCaml got this one right. I think bindings should be ordered. In Haskell, it's not just the explicit recursion, but by having bindings be ordered, it allows us to control our namespace just a lot better. So let's see another example of why we might want this. So here in Haskell, if I import data.set and I import data.map and then I talk about empty, I get an error because empty is ambiguous. Do I mean data.map's empty or data.set's empty? Over in OCaml land, I can open set.makeInt. Let's not get into why there's like a functor application here right now. But I can do that for set and map, and if I talk about empty, well, I just mean map's empty because that's the one that's most recently in scope. Maybe I meant set's empty, in which case I get a type error. But this also means that if I have, say if I have some module that exposes something that I just don't care about, I can just shadow it later on, and it's just so much easier to program with. Ron has a point. So I'm saying something nice about OCaml. Ron, you usually react when I say something negative about OCaml.
So, I mean, I think the shadowing is like a complicated example. I think it's good to have shadowing, but like it's a little messy, and I can see why people wouldn't like the example on the right fully, right? Because it's like let equals empty. It's like a little, even if you see the ordering, it's kind of a little bit of a spooky action at a distance and stuff. But like I think there's actually a much stronger reason to want bindings to be ordered because it makes it easier to reason about your code, right? The reason for recursion to be explicit is because recursion is harder to think about. The reason to have ordering is because you're just reading things in definition order. You know, like that first one on the top of the file, what does it depend on? Nothing else in the file. The next one I read, what does it depend on? Only the things ahead of it. It's like a constraint that makes the code easier to reason about. And I think that's the primary reason why I think ordering is important. I like the namespace construction thing is useful, but I think the ordering, the reasoning thing is primary from my perspective.
Sure, I agree with that. There's a comment, right? Gergo.
So, yeah, because you said at the beginning that you're saying opinions and we should also say opinions. So this is just like, I want to say my opinion on this, which is that I think import shadowing, so when you, is the Goldilocks point in this design space. So basically, I think if you define empty in the left-hand side and then in the same module and then use it, it should be clear that you mean the empty that comes from the module that you're defining. I don't like the one on the right where imports are ordered. So I think, so you should think of all your imports as a set, but then the module you're defining is one scope deeper. And there is actually, as you know, but maybe not everyone knows, there is actually an open proposal for this that unfortunately I had to abandon for other reasons. But yeah, there is. It seems like there is community agreement from the Haskell side that that's what we want, because that proposal had gotten really good feed or uptake from community.
So that, I mean, I see what you're saying. The reason I still think ordering is good, at least for sort of this scope thing, I agree with Ron's point that there's also a reasoning principle, but sometimes you just have a module that exports a function that you just don't want and don't care about, and then because of that you end up with an ambiguity problem. And there's sort of, I mean, yeah, you can say hiding, but in practice I find that just kind of painful, whereas that pain doesn't arise in OCaml. It's just sort of a better world in that
But you
way.
get a different pain if your modules would have exported at the same type, because then you're not going to get a type error. You're just silently going to pick the second one.
Yeah. No, there's not one right answer here necessarily. I see. While the mic is in the back, let's.
There's another thing is that here the two are basically like imports just side by side, but often one of them is going to be much closer to your use point. Like you can have a local open, and the fact that it works the same if you have like some opens at the top and some opens like inside your function, even inside your function body, at whether like it's only the order matters, not the are they like the imports that you do at the top of your module versus that. So I think that in OCaml it's quite easy to think about because it's the same thing. Like it's just you have the list of opens beforehand, not you have a bunch of open at the top level of your.
But even then, I argue that local opens should be able to shadow things, but like interleave top level opens should not. I really think there's a difference between.
Sometimes they can be top level, but like at different points in your file. So you can have a local-ish thing where.
So if I can just sort of jump in. So I think this is fantastic. This is exactly what I wanted to happen. And now maybe there's a conversation that happens during the break. Because I feel like a lot of people are going to have opinions on this point.
Yeah, work?
Yes, I find that kind of annoying.
Yeah, so I was supposed to say that, but like actually, I think you got the point to quite extent. Like, if I have an open statement command, what would you call it, somewhere in the middle of my file, I don't want to have to look for it. If it happens just to shadow some name that I wanted to use from the top of the file, which was imported originally on the top of the file, where I would look for imports, right? And now I have to just scan and look for all opens on the way to find like where it's actually went wrong.
Yes.
If it's local, then I could agree shadowing makes sense. That's the perfect use of it. Maybe I would just use a different keyword then, but I think like a mixture of those two would work. And also in Haskell, I would just like to remind that in such a case, in the case, okay, maybe it was the previous example, you also have the where keyword, which...
We're going to get there.
Okay.
So I think in the interest of time, I'm going to move us forward, but I think we're already creating this nice conversation about sort of these two different language designs. So here's another example of kind of the same idea that in OCaml we can actually just shadow constructors and use them, and this is just kind of nice because it means that if there's a constructor again that maybe is imported that I don't really want, I can sort of cover it up. And this is convenient. Sometimes actually the shadowing is intentional, and I take something that might be useful but dangerous or somehow bad, and I shadow it with something that's useless on purpose, so that programmers can't access the bad thing, and this can be quite nice. Okay, I do want to move past just sort of the shadowing thing. I see there's some hands up. Is it just about shadowing? I think we'll move on. But let's have this conversation during the break. This is like, I'm very excited to see people's excitement on this. Okay, one slight variation on this on the OCaml side is that OCaml actually supports type-directed name resolution. And so if I have a type annotation on this F, even though the bottom A and B shadow the top A and B, I can still access them if I have a type annotation. And so there's no way to do this in Haskell because over here we can't have multiple different names introduced that are the same. But here it's fine. This, admittedly, I understand why GHC doesn't have this. It would be very hard to integrate this into the structure of GHC as it is. Although, interestingly, there is no way to live without interleaved type checking and name resolution in OCaml because of the way that the module system works. So the OCaml compiler must interleave the name resolution and type checking. So it makes something like this possible to consider. Okay, a bunch of small syntax things. I think there's probably going to be lots of opinions here. I'm just going to try to plow through. So we have camel case and snake case. I'm actually not going to stand with an opinion between these two, but I think we should use both. So those of you who have, maybe some of you have programmed in GHC. GHC has this wonderful naming convention where local things are snake case and exported things are camel case. This is really nice because it allows me to look at a function and quickly tell, should I be thinking of this as like, a polished exported thing or just sort of a local, maybe dirty thing? And it just makes it so much easier to read and understand the code. Haskell has where, and OCaml has let. So let me give an example of this. So I might have a function in Haskell that has some important stuff and then some fiddly little details. This is lovely. It means that at the top, I can just see exactly what I want to see, and then if there's a bunch of supporting details that need to be there because it's a real program, I can write those, but they're down below, out of the way. And it's something that I really miss in OCaml. OCaml, sometimes you have a function, and the first 20 lines of the function are just sort of throat clearing and getting rid of, sort of setting up auxiliary structures before getting to the interesting bit. And so Haskell can tend to avoid this. So I still really miss where, and I think OCaml should get it. But only once we have purity. If we had where and there were side effects, then what order do the side effects happen in? That's just really awfully confusing. If we're working in sort of the pure subset of OCaml, and we can track that, then having things sort of appear a little bit out of order in this way makes a lot of sense. And note, this doesn't require laziness, right? It just requires purity.
Will you touch on freestyle?
No. The question was, will I touch on point freestyle? And no, I'm not really going to get into that. Okay, indentation sensitive versus white space versus white space agnostic. I don't know. I go back and forth on this. Both are kind of annoying, right? Like, we've all spent a lot of time, like, with, in a Haskell, or Haskell programmers have all spent time, something just doesn't work, and then you don't know why, and you're like, I just need another space here. That's kind of sad. On the other side, in OCaml, there's a lot of keywords, and they're kind of annoying. I don't know. So Haskell has, I count 5 namespaces for modules, variables, constructors, types, and type variables. Some of these are uppercase namespaces, and some of these are lowercase, so you can divide that up a different way if you want to. OCaml has 11 namespaces that I could find, where you can define the same name, although some of these are capitalized, some of these are lowercase, and then some are oddly both. Module types can be both uppercase or lowercase. Type variables can be uppercase. No one ever does that. So this is just kind of a mess. I think both of these are bad. Let's just have one namespace. It means that names have to be a little bit longer. Maybe 2, so one are capitalized and one's lowercase. I'm okay with that. I think going beyond that is just confusing because it means now every time I talk about something, I have to specify what namespace thing I'm talking about. So maybe no one likes that idea, but I find the divided namespaces to be really quite annoying. Okay, talk a little bit about implementation. So OCaml is just so much faster than GHC. So the OCaml compiler builds from scratch in under 5 minutes, and that's like the production-ready one. The development version that I usually use takes about a minute, and that's for building the Bootstrap compiler and then building the stage 1 compiler and the stage 2 compiler and all of the libraries. It's nice. GHC, the last time I tried, it took, I think, 25 minutes. Often it said, well, that's the optimizer working. Even with the optimizer turned off, it takes a lot of time to compile Haskell code. So I think GHC has some catching up to do here. On the other hand, GHC has this typed intermediate language, which provides this beautiful safety net of adding new features to the language, and where we can know that that the feature is sound if it can desugar down into this typed intermediate language. So that is really quite nice. The flip side is that's part of what keeps GHC a little bit slow, and it also, I think, makes more of a challenge in developing features. So there's sort of a cost-benefit trade-off in that every time we add a new thing to GHC, we sort of have to prove that it's type sound, whereas in OCaml, we can just kind of add it and hope. And so maybe sometimes that's the better choice. Another big difference in the implementation is things like this. So GHC is completely covered with these notes that give overview to different subsystems, and it makes GHC much easier to work in, and is a really nice thing. And so I have now snuck a couple of these into the OCaml compiler. If you look in the OCaml, there's 1 or 2 in the upstream compiler. I think there's a few more in Jane Street's branch, but expect more of this in the OCaml compiler as I keep working on it, because these are nice. Quick comments about the community. So one might think, these are, how is the community different? The communities are really quite similar. Both are really welcoming. I was in particular worried coming into OCaml. Was like, oh, here's this Haskeller coming in. What's going to happen? And I didn't feel that way at all. The OCaml community has been very welcoming, and I just find a good collaborative spirit in both. One thing I've enjoyed sort of piloting is in both communities, I've helped form sort of a proposals process by which the community can contribute and build things, build new features into the language. Anyway, just wanted to sort of dispel any thoughts, oh, those people over there, they're not very nice. I think that that's not true in either direction. I'll talk a little bit about the funding models of the two communities. So both places now have foundations. There's the Haskell Foundation and the OCaml Foundation, both with a bunch of sponsors on both sides. So that's great, right? We have communal places where funding can be drawn into and then dispersed from to develop new features and support the languages. They're a little different in structure, right? So the Haskell Foundation has a full-time paid executive director. That's at some point, there we go. That's Jose Calderon at the moment, and so his full-time job is thinking about ways to support the Haskell community. The OCaml Software Foundation is a volunteer organization currently directed by Gabriel Scherer, who also puts in a lot of time in thinking about the OCaml community. But this is kind of a difference. It's still sort of early days in some sense to know what's the more sustainable thing going forward. But I just sort of wanted to highlight that there's more than one way to do this. So there is a really big difference between these two communities in that there's no escaping the fact that Jane Street is a big supporter of the OCaml community financially and in other ways by coming to conferences such as this one. And there is no equivalent. There are a number of companies that are players in the Haskell world, but no company with prominence like Jane Street's. Jane Street does this because it's good for Jane Street. It's also good for the community. But we don't do it just out of benevolence, right? We do it because we reap the benefits of doing it, and we get to be involved in the community, and we get to help others build things such as multi-core OCaml, which mostly happened outside of Jane Street's walls. And so there's good reasons to do it. I would be very excited to see a company come in and try to fill that role in the Haskell community. I think that for Haskell to continue to thrive, we need sort of more of this. So if you work for a company that uses a lot of Haskell, think about maybe upping your contribution. Right? There's a good template for this, and a good Jane Street I think can show how this can be done. I would love to talk to people about how that works for Jane Street. I'm going to make a shameless plug. This is about another way in which Jane Street is sort of showing its commitment to both of these communities in that we are hosting a Haskell hackathon in February. So this is going to be sort of a North American equivalent of Zurich Hack that the Haskell Foundation is organizing, Jane Street is hosting. So you can find information on the Haskell Foundation website about this. But this is yes, it is at Jane Street, but this is a Haskell event that I'm looking forward to attending.
Will all the participants be kidnapped?
Only some will be kidnapped. Okay, so I want to end with a controversial proposal, right? This has been all about creating conversations between the communities, and some of these conversations have already started, which I'm super excited by. So one thing that I've been aware of as having some amount of organizational ear in both communities is that the Haskell Symposium and the ML workshop are sometimes looking for more content. So maybe they should be combined. So I do have a name up here. That's just sort of a name I came up with as part of this talk. But wouldn't it be great if instead of having Haskell talking about research ideas about strongly typed functional languages and the ML workshop talking about other research ideas about strongly typed functional languages, maybe we should just have one room where all of that happens. Now, we still need other rooms where very Haskell-specific things, or very OCaml-specific things, or very other ML-specific things can happen. And so I think that should be there too. But the idea that maybe the sort of the higher level, the peer-reviewed research gets put together in one common stream, I wonder how that would work.
So technically, yeah, it isn't the ML workshop, it's the ML family workshop, which maybe is not an appropriate name to satisfy well, what you desire, but that actually does cover a broad range of languages already in its
but not
core.
Haskell.
It does. Haskell is allowed is in scope for the ML family workshop.
The last time I looked at the ML family workshop, it had strict.
Oh.
The ML family workshop says that it's for strongly typed, inferred, functional, and strict languages, which seems to quite loudly say Haskell is not welcome here. Well, then that's maybe something. So I'm not currently on any of the organizing committees that might be able to affect this, but I'd be happy to talk to folks about making it a reality. I see some hands up there. We're sort of out of time right now, so I'm just gonna. I think this might be the last slide. Yes, I want to create new conversations, and there we go. Thanks very much.
You remind me, we have OO Haskell or something a long time ago. I think it's dead, right? I'm not sure anyone remembered. And in Jane Street, can you talk about the object-oriented programming part? What kind of situation you use object-oriented programming that solves the problem better than Haskell, which is a pure functional programming language? Do you have some situations or real-world project?
So you're talking about the object system in OCaml? Sorry.
Yeah.
Generally, in Jane Street, we do not use the object system. There's certainly people in the OCaml community that do, but I'm the wrong person to speak about that.
Okay.
Sorry.
I've noticed the Haskell Implementers Workshop is no longer at ICFP, and I really miss that. As someone that's working on the OCaml compiler, it would be nice to have a combined compiler sort of implementers sort of workshop.
That's an interesting idea. So Haskell Implementers Workshop is definitely alive. It was moved to Zurahack this year, where sort of more of the Haskell implementers are sometimes than ICFP. I don't know about the conversation there about whether that's going to stick or not. I'm not aware. But I just wanted you to know that it's not gone. It's just elsewhere. Well, it's not here. But as we continue to think about this, I think that's a good point.
Actually, I have a technical comment, not a question. So you had an example where you show there's GADT programs that are accepted by the OCaml compiler, but not the Haskell, because they use a different type inference algorithm. But if you look at the ambivalent types paper more closely, there are also programs that are accepted by the GHC, but not by the OCaml compiler. So I'm just saying that because we are at the Haskell Symposium, I feel obligated to say that the type inference in GHC is not necessarily weaker than the OCaml, but they have different trade-offs.
Yes, that's a good point. Thank you.
All right, let's thank Richard again for this great talk.